Now, before we dive a little bit further into operations we can conduct on vectors and matrices and Bra and Ket vectors and orthogonality and anything along those lines, let's consider and dive a little bit further and explore a little bit further the concept of matrices. More specifically, let's begin by talking about transposing a matrix. Transposing matrices. Right. Now, when we consider transposing a matrix, any given matrix in general, kind of notation, say you're given some matrix A, is that once it's transposed, you just merely write it as a T. So for some matrix M, it is transposed and becomes M to T. And so let's say your matrix A is 1, 2, 3, 4, 5, 6. Now when we transpose it, we want to take its dimensions of n by m by n, dimensions of n by n, and flip them such that its dimensions are n by. And so what does this mean? So as a quick reminder, whenever we do have some sort of matrix, the dimensions are written in such a way such that the rows are always come first and your columns come second, right? So in this case, when we have an n by m matrix, all of a sudden we are taking the number of rows and we're turning that into the number of columns. We're taking the number of columns and turning that into the number of rows. So in the case of A, let's consider what that means. So quite simply, we have a given matrix right here, and its dimensions are 3 rows and 2 columns, a 3 by 2 matrix. Now, A transposed, on the other hand, based on what relationship we've kind of defined here, A transposed will have dimensions, and we flip their places, 2 by 3. Right. Now, let's go on a little bit further, and let's consider the placement of these elements. We already know that there are going to be 2 rows and 3 columns, but where do these specific numbers themselves go? Right. So we can begin in several places, first of all. And there are, of course, multiple ways to consider this, multiple ways to do this, but one of the ways that I personally prefer to do it is if we look at the row, we take a look at the first column in this case, then the first row in A transposed will be equal to your first column. So in this case, the elements in your first row are 1, 2, 3, and your second column becomes your second row, 4, 5, 6. And that is simply how you would transpose a matrix. Now let's do a little bit of practice. Let's look and see and make sure that we've got this, essentially this concept down pat. And let's take some matrix B is composed of, say, 2, 4, -1, 0, 9, and 8. And let's talk about what B transposed is. Right, B transposed. And I'll give you a few seconds. If you want to pause the video now and just solve it on your own, that is perfectly okay. If not, we will resume in about 3 seconds. Alright, so first things first, and I'm assuming that you've already either paused the video and solved the problem, or that you have, or if you want to, kind of go ahead and make sure you know this concept a little bit better. So first of all, we're going to take a look at the dimensions of your matrix B. Now the dimensions, as we said before, come in rows times columns, right? And there's 2 rows here and clearly 3 columns. So the dimensions of B is 2 by 3. So therefore, the dimensions of B transpose should be 3 by 2, right? A 3 by 2 matrix. Alright, second, when we take the same order that we kind of said earlier, your first column becomes your first row. So your first column to 0 becomes your first row. Your second column becomes your second row, 4, 9. And your third column, again, follows the same process, becomes your third row, -1, 8. Right, and that's basically the process of transposing a matrix. Now let's consider what this means in the case of bras and kets. Now keep in mind that bras and kets are essentially vectors, right? Either one column or one row, sort of matrices, and they are special cases of matrices. Special cases of matrices. Right, and your bra vector A is defined as being some single rowed matrix, whereas your ket vector A is essentially just a single column, right? And so when we consider transposing either your bra or your ket vectors, there comes an interesting relationship and an interesting sort of pattern that emerges. And so let's begin by transposing. More specifically, let me just shrink this. Let's begin by transposing, say, your bra vector A. Right, and we'll say A is defined as having elements 3, 5, 4, and 0. Now, when we transpose A, we have A transposed, right? First things first, we take a look at its dimensions as 1 by 4, and so therefore, we're going to be looking at a matrix that has 1 column and 4 rows. Once again, we switch the dimensions. Now, following the same steps that we said earlier, your first column becomes your first row. So 3 becomes your first element here, your second column, second row, and so on and so forth. Now, what's curious though, and what is quite interesting, what arises from this is that if we take a look at this new transposed matrix that we have here, this interesting bra vector, we notice that it has a single column. And that is fundamentally the definition of some bra vector. I'm sorry, some ket vector, right? By the name of A. And if you notice, if you write A as a ket vector, simply put, this is the result that you get. Therefore, the relationship that we have here is that some ket vector A is equal to some bra vector transposed. And similarly, if you do it the other way around, right? If you start with some ket vector A, we'll just simplify it 1, 2, and 3. Interestingly, if you transpose your ket vector, this, right, becomes your equivalent bra vector. And therefore, when you have a bra vector, on the other hand, that is equivalent to your ket vector transpose. And that is the relationship that we can kind of define and pull from what we have here. Now, continuing down in the thought process, the line of thought, the concept of bra and ket vectors, let's circle back to matrices, and more specifically, the general definition of matrices, where you have, again, some number of rows and some number of columns. Now, what's curious, though, is that we have defined a matrix in general as being composed of a number of rows and a number of columns of some sort. But if we break it down, let's say we want to break it down into certain quantities, and we group them by rows and so on and so forth for whatever number of rows there are, and we'll call this matrix M here, right? Then each of these rows corresponds to a single bra vector. We can write it, in fact, as a bra vector. And so we can say it's a matrix of, elements that are essentially in themselves bra vectors. So what do I mean by that? So let's say you have 1, 4, 5, and then 2, 3, 1, and then you have 9, 2, and then 0, and then let's say 6, 2, and 0. Right, and for whatever number. So let's say this is your matrix that we have right here, and we can write them as individual bra vectors. So some bra vector A and some bra vector B, some bra vector C, or alternatively, we can number them instead. Let's number them. That might make more sense in this context. So 1, 2, 3, right, and some bra vector A, 4, right? And so we can actually rewrite this matrix M to be merely composed of all these bra vectors. And this will come back a little bit later. And A, 4. Alright, so that kind of wraps it up for just transposing a matrix and just the general relationship between matrices and vectors in a sense, and bra and ket vectors. And of course, if you want to, you could also group them by columns and turn them into a series of ket vectors. Either way is functional. Alright, so that does it for today. As always, if you have any questions, just feel free to visit the Q-munity Tech website. As always, stay curious and keep on learning.